So let's start. We are going to talk about magnetic materials starting from today. In this PowerPoint set, before we classify magnetic materials, we have to define what is induced magnetic dipoles. And we need to find a way to quantify such induced dipoles. And when we induce magnetic dipoles, those dipoles effectively generate new current sources. Okay? We also have to find a way to classify and quantify this induced current sources. So I will spend most of the time in the first subsection, static magnetic fields in materials. We need to find a way to properly formulate the materials using simple parameters. Now, if you still remember, in electric dipoles and in electric materials, we used epsilon r, the relative permittivity, to explain the material using a single quantity. In magnetic materials, we also want to find the relative analogy. So we use a relative permeability, right? So once we have a mathematical tool to describe magnetic materials, we then classify magnetic materials. Depending on the quantity of the relative permeability, we can classify the materials accordingly. And finally, we need to talk about the boundary conditions for magnetic materials as well. Right? So as you can see, in the first subsection, we have lots and lots of titles, but essentially, we want to find how to quantify the induced magnetic dipoles, and the result of these dipoles will give a new term called magnetization current. And there are two types. One is the surface magnetization current. Another one is the volume. Okay? So we need to have proper mathematical formulations for both of them. And in the end, we will introduce a new vector field quantity called the magnetic field intensity. So in all textbooks, the magnetic field intensities will be described by using the capitalized H vector. Okay. So for these, I want to save for next Monday. So today we might be able to finish the top 3 topics. Right? Okay, up front, how to create a current conducting closed loop. And before today, in the examples, we just assumed we have a metallic wire which forms a closed loop, but then we have a constant current flowing. But that's really superficial because, in the real world, without a battery, how can you generate a non-stop current? Right? So that's not very practical. So if we look into the atomic sense, in a very microscopic view, the way to create a closed loop current conducting device, the magnetic dipole, is, well, if you have the nucleus and you have an electron orbiting the nucleus, the electron carries a negative charge, right? So in this case, if the electron is orbiting the nucleus in the clockwise direction, it's equivalent to a positive charge orbiting the nucleus in the counterclockwise direction, right? So if you have an orbiting electron, that is essentially identical to a closed loop with a constant current, right? So in a sense, if you have orbiting electron, or maybe the nucleus is spinning, but the nucleus is not ideal, completely uniform, then you form a very small closed loop current. And then you have the magnetic dipole. Okay? So this is saying, well, if you apply external magnetic field, that magnetic field will force the electrons to orbit. Or if that external field forces the nucleus to spin by itself. These are the two potential ways to induce magnetic dipole moments, right? So in this case, with the presence of external magnetic field, the electrons start to orbit, so it is equivalent to a positive charge orbiting in a counterclockwise direction, and therefore, again, we use the right-hand rule. The positive charge is orbiting this way, so it's producing an induced magnetic dipole pointing upwards. So the definition of magnetic dipole is still the same. Basically, your magnetic dipole moment, which is a vector, is in the surface normal direction using the right-hand rule, and then you have the amount of current times the area. Right? So basically, if you have a magnetic dipole moment, the unit is amp times meter squared. Okay. Now basically, usually a bulk material has no non-zero magnetic dipole moment without externally applied field. Okay? For typical materials. Of course, we have permanent magnets, but that's another story, right? So basically, for typical materials, you might be able to induce magnetic dipoles when you apply external field, just like the dielectrics, okay? All right, so now we introduce a new terminology, which is called the capitalized M vector, which is called the magnetization vector. It's very similar to polarization vector in dielectrics. So in magnetic materials, if you have the capability to induce magnetic dipole moments, we are only trying to count how many magnetic dipole moments are there within a very small value. Therefore, basically, the magnetization vector is just the sum of all the induced magnetic dipole moments within that small value. So it's a value density of the induced magnetization dipole moments, right? Now the unit for M, capitalized M, is ampere per meter, right? Because you have M divided by delta V. Delta V has a unit of meter cubed, right? So you divide this by meter cubed, and you have ampere per meter, right? So when you read the unit, this is like saying, well, this is more like a line current density, right? J, the current density, is how much current you have per unit area. But now you only have a meter in the denominator, so this is like a line current density, right? So this M multiplied by certain length will give you the unit of current. This is more like a line current density. Okay, so I'm not going into the details, but once we have the induced magnetic dipole moments in certain material, if all of this vector sum does not go to zero, remember, all the magnetic dipole moments are vectors, right? So you can have lots and lots of induced magnetic dipole moments, but if in the end, all the summations of the vectors go to zero, then it's not a magnetic material. But for a magnetic material, which means when you have externally applied field, and pretty much all the induced magnetic dipole moments would line up in the direction of your externally applied field, and therefore the vector sum is non-zero. Then you have a non-zero magnetization vector. So in this case, you have a magnetic material, right? Where you have a non-zero capitalized M vector. If that is the case, well, all we have to do is replace the current density in our previous Biot-Savart derivation, right? If you have some current loop, all the induced magnetic dipoles would sum up to form a current loop, right? So once you have a current loop, all you have to do is put into this formula, and then you have the resulting vector magnetic potential, right? So once you have a current conducting loop, it will produce magnetic potential and therefore the magnetic flux density. I don't want to go into the mathematical details, so if you want to know the math, please read section 6-6 in the textbook. It provides step-by-step derivations. But what I want to do is I want to extract the end result. But once you have a non-zero capitalized M vector, which means you are dealing with a magnetic material, in the end, once you have this magnetization vector, you will have the vector magnetic potential. But the M comes in two functions. One is, you notice the first term here is a volume integration. It's a three-dimensional volume integration, okay? And the second contribution is a closed surface integration. So this means if you have a non-zero M, if you perform curl operation, if it's still non-zero, then you have a contribution to the value. So this term, curl of M, is called basically the volume magnetization current. On the other hand, M, a non-zero M making a cross product to the surface normal, is called the surface magnetization current, right? So the classification is very simple. Now you have a closed surface integration, and this term, if it's not zero, this contribution is called the surface term. And this is the volume integration. If curl of M is not equal to zero, then you have a volume magnetization current term. Alright? So for the following slides, we are merely going to compare these terms with the electrical charge densities and then we want to confirm these are indeed the right mathematical formulations. Okay? So if you still remember, for a dielectric material, once you have externally applied E field, you induce electric dipoles. And then you have the polarization vectors. The polarization vectors are denoted by capitalized P vectors. In electric materials, dielectrics, we also have the surface and the volume charge densities, right? So if you still remember this, P dot the surface normal gives you the surface dipole charge densities, and the negative of divergence of P gives you the volume charge densities. Now we move into the area of magnetism. We have a very similar result, but the only difference is now we have current densities instead of charge densities, right? So the surface magnetization current density is and the magnetization vector, making a cross product with the surface normal. The volume magnetization current density is the curl of the magnetization vector. Now, if you still remember, near the end of the previous PowerPoint set, I showed you it is actually very easy to convert from electricity to magnetism. All you have to do is interchange P by M and dot by cross, right? Look at it. If you understand E field very well, all you have to do is replace P by M and dot with cross, and then you have the result, right? So divergence, you replace it by curve, right? So up to now, when you have induced magnetic dipole moments, in the end, if all the vector sum does not reach to zero, then you are dealing with a magnetic material. For magnetic materials, you have two potential sources of current densities. One is the surface, one is the volume current densities. Okay? So in the following, let me try to qualitatively prove this is the right formulation for the surface magnetization current density, right? So here, I'm showing you a magnetic material. Your externally applied field is out of paper. And here we assume this is a nice magnetic material, so all the induced magnetic dipole moments, and therefore the resulting magnetization vector, is also aligned to your externally applied B field. Okay? So this is a well-behaved material. Now, if you look inside in the microscopic view, everywhere we would have orbiting electrons, right? And therefore, every place we can draw some small current conducting loops, right? Now, because all the magnetic dipole moments are aligned with your externally applied field, so all the currents are actually, well, in this case, counterclockwise, right? You follow the current direction using your four fingers, and your thumb points in the direction of your applied field. Okay. So everywhere you have a counterclockwise current conducting loop. So if you ask yourselves, well, if I am inside, for example, this point, right? Exactly at this point. Now this point is connected to two dipole loops. One is this one, another is this one, right? Exactly at the connection of this point. And then you ask yourselves, well, at this point, what is the net current? This is tricky because at this point, the left current conducting loop is giving an upward flowing current. But at this point, the contribution of the current from the right loop is pointing downwards. Right? And assume this is a very uniform material, the amount of current for this loop is equal to the amount of current provided by this loop. So basically, at this point, the net current is completely cancelled out. Okay? So this is the essence. If you have a very uniform magnetic material, you apply an external field, and everywhere you produce the same magnetic dipole moment strength, and they cancel out completely in terms of current. So where in this material do you expect to generate the effective current density? Everywhere inside, the currents are just cancelled, okay, by different adjacent loops. So only at the surface, at the interface, where you have the ability to create magnetic dipoles, here inside the material and not outside, right? Here you have no magnetic dipoles, but here inside you do have them. So only at the surface would you anticipate to have non-zero current densities. So in this case, at the surface, you have two surfaces here. So you expect to have two surface magnetization current densities, right? Apparently, for the right surface, due to the flow direction of the currents, they are counterclockwise. So eventually, along the surface, you have a current flowing upwards. Okay, so let us check whether this cross product makes sense. And in this case, it's out of paper, right? So M is out of paper, and now for this surface, your surface normal pointing outwards is pointing to the right. So your N cross AN, right? N is into your eyes, cross AN is flowing upwards. At least, up to now, it agrees with our figure, and that formulation seems correct. What about this surface? Well, this surface, due to the current flowing direction, it would give you a downward flowing current density, right? But the mathematical formula is still the same. So in this case, M still pointing into your eyes, but now the surface normal is pointing to the left. So this N cross AN is now pointing downwards. So that is okay. We have double checked. This simple mathematical formulation holds, right? It holds.